So ladies and gentlemen, welcome to the next video segment of the lecture User Interface Engineering, Chapter 7 on Usability Evaluation. By now we have heard about how to conduct experiments, how to do empirical evaluation, and user studies are one means of doing that, and a very prominent one. And let's assume we have done our study and the data is recorded and logged, and now it's time to analyze the data and to do some statistical evaluation to find out how good we were, for example, how fast we were, how many errors were made, which conditions was perhaps the best. So basically, descriptive statistics is devoted to the topic of describing and exploring the data we have collected so far, and it tries to summarize data in meaningful ways. So imagine you have lots of data logs you have recorded, lots of task completion times or error rates or anything else from users, questionnaire data from perhaps dozens or hundreds of users, and you would like to reduce it to few numbers, to few meaningful numbers and some data which you can report and talk about and which you can interpret. And this, of course, this descriptive statistics includes all types of graphs you might have seen already in scientific papers or even in newspapers sometimes, if you think about election results, and other types of visual representations. So, important step of the data analysis is to examine or examine the distribution of the data. That's very important. So how is the data actually distributed, and then to do tests on the assumptions or prerequisites which are necessary for later on doing the statistical tests. So for example, you test whether there is a normal distribution of the data or not, and whether you can apply a certain, say, parametric test or not. Some terms at the beginning. So population versus sample. The population is the overall set of entities we would like to measure. So in HCI, this is a user typically, and a user in that case in a means of a population will be the entirety of all potential users. And this is, of course, a theoretical construct, because we do not know every user who will ever use a particular mouse we want to test in our study now. So this, there would be the mean would be mu, and the variance would be sigma square, which is a rather abstract value, and maybe a bit better and approachable is the standard deviation here. So standard deviation sigma, which is the square root of the variance. So with the mean mu, you have the average values, say what the users like how fast they are, for example, the average task completion times of potentially all users using a particular mouse, for example, and of course the standard deviation provides to you a measure of the amount of variation or dispersion of a set of values. That means how close are the values to the mean? That's the question. So, and the mean, of course, is also called the expected value in a given set of data, and the highest standard deviation indicates that the values are rather spread out over a wider range, and smaller, obviously, that there is a small range around the mean value. Typically, we don't test the population in its entirety, because it's even theoretically practically impossible, theoretically only, to be thought. And therefore we have a sample. That means it's just a collection, in this case, of potential users we would like to test. Maybe we have just 24 users or 30 users we would like to test. And so this is a set containing the entities we actually measured. In this case, these are our study participants. Of course, we don't measure them, but we measure something, what they do, for example, task completion time. This can only be a subset of the population. It's also called X, the mean X, and the variance here is S square, and standard deviation S. And we say the number of samples we have N, and this is a famous N. And of course, there's a lot to say about how big this N should be to be resulting in some ecologically valid results. But this is an extra topic. By the way, in this section on the data analysis and statistics, I can really only scratch the surface and throw in a few terms and give a rough idea of what it is all about. And if you're interested in more details, I recommend books like this one to you, which is a famous book by Andy Field, Discovering Statistics Using SPSS. This book also exists with using R. And Andy Field is really a master of describing statistics and making this approachable for you. So if you have not looked into that, it's very nice, it's very graphical, it's nicely done, this book, and I can only recommend that to you. And of course, you can spend a lot of days or even weeks or even months doing statistics. So forgive me if I'm really superficial here and just scratch the surface. And of course you find a lot of sources later on the bibliography to help you out if you really have to do a study and to do that. And by the way, just as another point, it has also a lot to do with experience. So of course you have to do experiments, you have to actually get hands on the data, get your hands dirty, say using R or SPSS as a tool, and only then you're able to understand the approaches in depth. So we have some measures of central tendency. One is mean, obviously the average value, which is the sum of the values divided by its number. As you know, the median is the middle data value, so which is exactly there where half of the data is lying on this side, on the left side, and half of the data is lying on the right side. And the mode is the most common data value. Say you have a survey and you ask people for something, maybe their preference, and they choose this particular value, and this is then called the mode. And then more interesting, we have measures of variability or dispersion, and this one example is the mean absolute deviation. That means you have the mean is the sum of all the deviations divided by the number of your sample. And then you have the variance, we already talked about that, so S square, which is the same basically, but it's just squared divided by n minus 1, and standard deviation, which is the square root of the variance. So these are important, in particular the standard deviation, important values we use in statistics. Of course, you would like to graph the data to show it in some visualization. And this is what you often do as a first step after you have collected some data to look at it. You can use histograms, which is often the case. You can use box plots or stem plots. So there are several possibilities to do that. And even just a simple bar chart might do. So you get a feeling for the results and the distribution. For example, are they normally distributed? So do you have this typical Gaussian curve here or not? Are they somehow skewed in any direction? Are there outliers? Maybe we would have some values here or not. And that's important. Here's an example of such a normal distribution. In that, so you see like this Gaussian distribution here, and this is an example. Say you have certain values, in this case perhaps a certain frequency, whatever, distributed over a sample. And the idea is to detect the relationships in your data. And one important part for inferential statistics is to test hypotheses. So given the characteristics of our sample, in this case maybe given the age distribution, or given the height or weight distribution of a population, or in our examples, given the task completion times of all the participants in your data set, we would like to infer some characteristics from that. And then, of course, we have to assess how sure we can be of the results, which is then done with significant tests. So are the results really significant, or in a word meaning, in the semantics we know from daily life, so this is really a significant effort, I did a lot or so. And of course, this is very comparable to what we then do in statistics. I come to that in a minute. So for hypothesis testing, the idea is basically to derive a hypothesis from our observations or model. In our study I was using throughout this lecture, we thought that, or we had the hypothesis that spatial interaction is faster than touch. That means we assumed that techniques involving the mobile phone, spatial movement of the mobile phone to zoom or pan in this AR space are faster than in any of the touch conditions or the touch condition. And then we formulated a testable hypothesis, H1, based on measurable properties. So we, for example, say that the mean value between the spatial condition and the touch condition is existent. So there is a difference, the difference between the mean values of the spatial and touch conditions are existing and are of some value d. That's the idea. The null hypothesis, just a moment. So from that we can derive the null hypothesis H0, and this would say there is no difference between a value, maybe the task completion time in our spatial condition and in the touch condition. So this would be the null hypothesis. So there is nothing to observe, no difference between them. And the idea is now to construct a sampling distribution, assuming that this null hypothesis is true. So if you have a distribution, that means, say, 24 participants with their collected data on the task completion times, where for which we first of all assume that there is no difference between them. So this is what we do first of all. Then we run the experiment, we collect the data, and this is the sampling statistic X. And so these are just the individual values of the participants combined and aggregated. And we then calculate the conditional probability of X given this null hypothesis. So this is the data we have, and how likely is it that we measure X if H0, the null hypothesis, is true? Yeah, and this is the likelihood. And you can imagine if this likelihood P, the probability, is small, that means we can reject the null hypothesis and thereby indirectly confirming our initial hypothesis. Just to say that again, so if there is a very small likelihood, probability that we can measure X, and this is a given, if H0 would be true, then of course we can reject it. So that's the idea basically. And yeah, so for example, we figured out that in our case, across all conditions, the spatial conditions, the times measured minus the touch conditions in our experiment data, that this probability was smaller than 0.05. So there is evidence that spatial interaction is faster than touch because we could not confirm the null hypothesis. The null hypothesis is a statement that the experiment tries to reject. Yeah, that's the idea, because we would like, since we can't test this one, we can only try to reject the null hypothesis. That's the idea, to nullify it basically. typically, but not always, stating that there is no effect or no difference. That's the idea. In a null hypothesis, a typical null hypothesis says there is no time difference between the spatial condition and the touch condition. There is no difference. That would be a typical null hypothesis. Or there is no difference in the error rate given mouse A and mouse B, for example. And so instead of proving the hypothesis H1 directly, we try to disprove the null hypothesis. That's just to say it again, very important. And the result of this hypothesis test is significant if it is less or equal than a certain predefined significance level, which we chose before the study. So there's a certain level, alpha, let's call it alpha, and if the probability is smaller or equal than this alpha, then we say it was a significant result. So this can be 0.05, and there are different levels of, for example, highly significant, which is then smaller. So this is called the p-value. We talked about that already, the probability of measuring at least that x, so the given data set, if H0 is true. Now we have to interpret the results. So rejecting the null hypothesis. So if the probability is very low, given, so smaller than a significant, this significance value alpha, then we can say, correctly say, if the null hypothesis is true, there is only a probability of p of getting our results. Yeah, that means we can only say that yes, the null hypothesis could be true, but only with this very small probability given the current data. And it would be wrong to say there is only a probability of p that our results are an error. And even more important, which is also wrong, there is only a probability of p that the null hypothesis is true. That's not correct. It's just if the null hypothesis is true, there's only a probability of p of getting our results x. And if you're not able to reject the null hypothesis, so if it is, there's no significant value to be found here, so bigger than that alpha, there's no decision possible about the null hypothesis. This is one academic treatment, and another one by Niemann and Person is we may accept the null hypothesis for now, but new data could change this. So we can't really tell anything about that. And it's wrong to say H0 is proven to be true, or the experiment indicates that the null hypothesis is true. And that's very important to consider in your mind. So remember, always test indirectly your hypothesis. That's the idea. But now is the question, how can we compute that magical p-value? And there's some test statistic. And it's basically the ratio of the variance, which is explained by the model or the hypothesis, and the variance not explained by the model. So variance explained by the model. So basically this is the effect, and the variance which we cannot explain by the model. So the deviation, the error basically. A higher value means that the results are better explained by the hypothesis and less likely to be random. So if the effect is big and the error is small, we have a higher value. And so our explanation, or the variance explained by the model, is less likely to be a random. Yeah, the distribution is known. I wanted to say, if the distribution is known, the probabilities for each value can be computed, or of course they can also be looked up. So basically we can use different test statistics, and this depends very much on the experiment design and the data assumptions. For example, normal distribution or not normal distribution, which is important for parametric tests, for example. So there is a t-test, just to throw in some names. There are a series of f-tests or ANOVAs, for example, analysis of variance, and the chi-square test. And of course, there are lots of variations and details on them, and I just briefly guide you through some of them. So the exact equation is different for each test statistic, and there are different ways to calculate your magical p-values. Let's start with t-tests. It's a parametric test to compare two means, so based on so-called t-statistics, and this is just 2-by-1 designs basically. So you have two sets of data. So that means two sets of data. You can measure whether the two means are different. So it's just for one condition basically, and it's a parametric test, so it assumes normal distribution. And if you have between subject design, that means if the subjects are only doing one condition, then you have an independent t-test. And if you have a within subject design, that means if all subjects of your study or participants do the conditions, then you have a dependent t-test. So it assumes normal distribution, as I already said. And for dependent t-tests, difference between the scores for the two conditions are normally distributed as well. That's very important. And there are different tests available, like Kolmogorov-Smirnov, Shapiro-Wilk. And you can also look at the histogram, which helps a lot to see the normal distribution and to test your assumptions, basically. The measured data, this is also important, is at least at the interval level. So it's not ordinal data. So you can't use it for ordinal data like just saying warm or cold, for example. For that, it's not suited. And for the independent t-tests, you should also assume a homogeneity of variances, and that the measurements in different conditions are independent. That's, of course, very clear, and this should be the case. If you have a between subject design and you split the group of people for say to participate in the two conditions, then of course they should be independent. ANOVA, the analysis of variance, can be considered to be a superset, or in other words, the t-tests are a subset of ANOVAs. It's a possible subset. They can be used, ANOVAs, for designs with more than two levels and also for factorial designs. So assuming, for example, we have not just one, but two or even three independent variables you would like to vary. Say you would like to test maybe two different or three different device designs, like three different mice, and on maybe three or two different screen sizes. That would be the second independent variable. And maybe you would even consider gender to be another independent variable. Then you would have three independent variables to test, so you couldn't use a t-test for that. In a way, it's a generalization, as I said, of the t-test, and therefore it can also be used for these 2-by-1 designs. The statistical or foundation for that is called the f-statistics, or also f-test. As I said, I can really just scratch the surface, and I'm also not an expert. I'm rather pragmatically using these approaches for our studies. The null hypothesis means all means the same, and alternate hypothesis, at least one mean difference. All means are the same, and the alternate hypothesis would say at least there is at least one mean which differs. And there's the ratio of variance between each group and variance within each group are set into relation. So basically, so we have the variance between each group and the variance within each group. So I have to apologize a little bit because I didn't do the slides myself. These were meant by some of my group, and at some points it's not exactly my mental model, so forgive me if I'm having different things in mind and then other things appear in terms of the wording. So that's the idea. So the ratio, just to say it again, the variance between each group and the variance within each group. These are these F values. And we have the same assumption as a t-test. So, for example, normal distribution. And ANOVA is quite robust to some violations. And there's, of course, a lot of science going on when to use it or when not to use it and what is problematic and what not, given a certain data distribution. There are different versions depending on the design. That means, is it a factorial design or not? How many independent variables are you testing? For example, three-way ANOVA or repeated measures ANOVA. And once you did an analysis of variance, you might find out there's a main effect. That means how a single independent variable affects the dependent variable. Say the type of, say, independent variable is spatial interaction versus touch interaction. This is the independent variable, and the dependent variable would be time, basically, that, or maybe error rate. Or here, interaction technique has a main effect on the task completion time. And there can be an interaction between two or more independent variables. That's what we call an interaction. That means, for example, an interaction technique is one independent variable, has an effect on task completion time. This is the dependent variable, depending on task complexity. And that's exactly, say, if you have task complexity as a second independent variable, or I gave you the other example of screen size. Say you have maybe this mouse and this is another mouse. We have two mice, so the independent variable 1 would be device, and the second variable would be screen size, small and big maybe. Then there could be an interaction between these two variables with regard to a dependent variable such as task completion time. That's the idea. And of course you have to find out more details and to interpret that. So the significance alone is limited in that regard because, of course, two samples, they have never the same distribution. If n is high enough, then the results are always significant. Also significance does not mean that an effect is big or important. That's very important. So for example, let's assume the spatial interaction results in certain values. Say on average it's 2.3 seconds to navigate, or maybe 20 seconds to navigate. And the touch condition could be 19.5 seconds. And let's just assume we would have significance, but the effect size would be very low. That means it's meaningful and often standardized way to measure the size of an effect. So the absolute effect size is maybe the smallest or easiest one. It's just the difference between the results. So between these 20 seconds on average and maybe 19 point something seconds. And you would see the absolute effect size is small, so even if the results would be significant, it wouldn't matter practically. And there are other different ways of measuring effect sizes, such as Cohen's d. That's the distance between the two means of two distributions here. That's one example, or the Pearson's R, the correlation coefficient. Also, you can use you can allow comparison and meta-analysis. That it means where you compare different studies or different results of studies and try to do a meta-analysis between them. But these are things, as I said, there's a lot of theory behind how you can measure effect size given on a certain distribution of your data. Just want to let you know that significance alone does not really matter practically. So for ANOVA, you can only find out that there is an effect, but you don't know exactly where the effect is. So that's an interesting aspect. So you have to test between which of the conditions the effect exists. For example, you know there is maybe an interaction between the interaction type and maybe the task type or the screen size. And you still have to find out between which conditions exactly the effect exists. So say, is it maybe only faster for the spatial one or not? You just know so one variable would be spatial interaction. Sorry, one value of the independent variable is spatial interaction. The other one is touch interaction. And you only know that the variable itself, that means the interaction type, has an effect. Yeah, and you don't really know which of the conditions actually causes it. So there are several ways. For example, planned contrast, when a hypothesis exists regarding the individual conditions. So you split the variance explained by the model into components or contrasts, as we also call them. So this method is also called planned components, comparison, sorry. And you compare two parts of the data. That's, you need to pre-plan that before the data collection. To say that a bit more practical, so we have some data, say this is our variable, maybe the interaction technique, and we had several interaction techniques. I think we had 4 different values in that, or 5 different values. And we could, with the planned contrast method, we can maybe summarize, for example, pairs of 2 of them, given some implicit information. For example, these two variants of our variable interaction technique, they share the characteristic that they are spatial. And maybe the others share the characteristic that you have to move the phone in the Z direction or so. That means you can somehow contrast different ways of grouping such, or to finding components within your one variable. So that's the idea. To then, at the end of the day, know what condition or what part of this variable actually causes this effect, basically. That's the idea. I'm sorry, I'm very tired today. All right, so, and another more often used tests are post hoc tests, when you don't have such hypothesis, when you are not when you don't know about the details of the individual conditions and can't summarize them and can't contrast them. For example, pairwise comparison with correction. This is one idea for the alpha, and there are t-tests with Bonferroni correction, 2K t-tests, etc. So basically you do that pairwise. You just try out all the combinations between the different levels. That's the idea. So instead having this implicit ad hoc and pre-planned knowledge of how to summarize parts of the data, you just do that using these statistical tests, t-tests. In general, it's helpful if you do some data analysis to choose the right test using this flow diagram here. And so in that decision tree, rather, you ask yourself, first of all, how many independent variables do I test? If I just have one independent variable, say just the interaction technique, or just the device, like mouse A and mouse B and mouse C are my independent variable, then I go to this branch here. And how many categories do I have? So if I have just two, like mouse A and mouse B, then I can ask myself, is it a within subject design? No. Then I can do independent t-tests, so I have a between subject design. So the groups are testing these two different categories or variants separately. Or if I have a within subject design, yes, then I can have can use a dependent t-test. So you see a t-test for a single independent variable, and then it's either Mann-Whitney or Wilkinson signed rank. Or if you have more than two categories, say 3 mice or 5 interaction techniques, if that is the independent variable, then we might make a difference between, again, is it between subject? If it is between subject, we can do ANOVA or Welch ANOVA. And if it is it within subject, that means everybody is testing all the interaction techniques. Say we have the variable is independent variable is interaction technique. We have 5 interaction techniques and every participant is doing each of them. Then we have a repeated measures ANOVA. And in our example, by the way, we had more than one independent variable. So we had the interaction technique as a dominant independent variable, but we also had the task type as another one, and even another one. I come to that in a minute. So with that, we ask ourselves, so if it is a between subject design, then we do a factorial ANOVA, or if it is within subject design, we do a factorial repeated measures ANOVA. And that's basically what we did. That means we had 3 independent variables. It was the interaction technique, the task type as I mentioned, and also the zoom level. I just didn't have in mind. So how far do you have to zoom? Do you have to zoom at all or not? That was the question. So basically we chose that part here, and since it was within subject and everybody was testing each condition, we had a factorial repeated measure ANOVA, or 3-way repeated measure ANOVA to be more precise. And that's a kind of diagram which helps you, this decision tree, to find the appropriate tests. And of course, at the end of the day, you have to report that in form of some graphs, and you should also be able to read these graphs. And this is a science in itself, because you can do things wrong in a very good way or not. And typically what you do include is the type of tests, at least in the text, maybe not in the diagram, but in the text, accompanying it, or in the figure caption, and some statistical value, the p-value or the effect size. These are typical measures you include. And for graphic in your text. And for graphical representation, you are often using these arrow bars, the whiskers, which are an important part of the graph. And they show the spread or of the results, so how they are spread basically. And typically you have maybe 2 conditions, like the spatial condition or the touch condition. In this case, this is aggregated data from all the spatial conditions and all the touch conditions. And you have maybe the total task completion time in seconds here. And this is a significance value, so the probability for this null hypothesis in that given data set. So it's highly significant in this example. And also we have a 95% confidence interval. So there is just a certain confidence you have, and you have to keep that in mind. And by the way, this is also a science in itself, how to choose a confidence interval, so I only scratch the surface here. Just for now, you know that 95% CI means confidence interval. So we found a significant main effect of the interaction technique. So these are the degrees of freedom. This is a value of the F statistic. This is a p-value, the probability value, which is below the significance threshold. And this is effect size here, partial eta squared. So we see a little bit the effect size and whether this plays a role or not in practice. And we also find a significant main effect of the task type, by the way, as you see here, and of the zoom level. And we found interactions between, so looking at the different independent variables, between technique and task type, between technique and zoom level, and between task type and zoom level, just in this example. And the post hoc tests then show the significant difference between the techniques themselves. So just to remind you, here we just say there is a main effect for interaction technique. And there is an interaction between technique and task type and zoom level. But we don't know which of the values themselves have a significant difference to another one. And this is shown here in this diagram. So this, by the way, is just to remind you, are the names for our techniques. I forgot the abbreviations myself, sorry for that. So, for example, move and drag, yeah, this is one example, move and drag, and move and rotate. And these two are significantly faster, it's about mean task completion times, than the other techniques. Like move and drag is significantly faster than D and D, forgot about this, and is significantly faster than DR and D, and it's significantly faster than AT, so to every of them. The same applies to M and R, and this is significantly faster than the first one, significantly faster to this and to that one. And between those, there's no significant difference between move, drag, and move, rotate. And these move and drag and move and rotate are in particular the one we can cluster and summarize as the spatial techniques, because they always include moving the mobile phone in different ways. And therefore, from that, we then interpreted that spatial movements are faster than touch interaction. Also, the questionnaire results can be depicted in some diagrams. So if you, for example, are asked about the speed and precision, so the felt precision and the felt speed, and the success, how successful the users thought they were, and they rated on a scale, and you see the mean score for each of the techniques. And of course you can also in a way mark statistical significance with these brackets in this example, and from the depending of course on the question, higher scores are better for speed and precision and success. So that means if the speed was felt to be higher, then this is obviously something better than the other one. So again, M and D and M and R were also felt the highest, as you see here, and there was a significant difference of how users felt, how fast they are between this condition, the M and D condition, and the other conditions, as you see again with these bars here. So this is a way of how to interpret, and then for physical and mental demand and frustration, of course, the lower scores are the better one. And you also see that, like, the frustration was quite low for the spatial variant, because it was so natural to move the mobile phone that way. Of course, for such questionnaires, it's always a bit questionable or debatable whether we can consider this data to be interval data, that means having an equal distance scale, or is it just ordinal data saying this is better or not so well? Like, I fully agree or I slightly agree. Yeah, this is just ordinal data, but we can't say this is the same like I disagree and I slightly disagree. So we can't really say is it an equal distance scale or not. By the way, here's also the data not normally distributed, so you have to take that with a grain of salt. Yeah, more robust but not as powerful as the Friedman test. So this is another variant to test questionnaire results such as Likert scale data. So here you have some special literature thrown into that section here to give you an idea and what we used here. And I particularly recommend, as I said, the field book, either Discovering Statistics using R, or it depends which book you have, or using Discovering Statistics using SPSS would be also a variant. So just to remind you, again, this was really only an overview on that, and I noticed it's hard to explain, even so how even so when you know how to apply it, it's statistics is not easy to explain. So there are better books, as I just showed you, to tell you more about that. All right, with that I'm done with that lecture, and this is just that for the year 2020 and 21, the section 4 about qualitative research and analysis is for self-study and is not relevant for the examination. So thanks a lot for watching this video segment.